Right, let's start proof. What we're going to do before we look at proof is we need a toolbox. And the toolbox is going to help us navigate through and actually do some of these questions that we'll see. So the first thing, so you need to copy this down. The first thing is that the idea of an odd and even number. If k is some integer, if I write k is just some integer. Okay, so you've got 1, 2, 3, 4, 5, 6, etc. If you've got 2k, then that just gives you 2, 4, 6, 8, 10. Yeah? 2k is always going to be even. However, odd, 2k take away 1. So this is going to give us even. 2k take away 1, or you can have 2k plus 1 will always give you an odd number. So 2 plus 1 is 3. 4 gives us the 5. 3 times 2 plus 1, 7, and so forth. So what we could do is, if we get a question where they talk about even or odd numbers, and we're going to model the situation, we can use k or n, I guess is another number, p, q are often quite used as well. Okay, we can model it based on this. An odd number is 2k take away 1, where k is some sort of integer, and an even set of numbers will be 2k, where k is just some sort of set of integers. Multiples, so if this is multiple of 7, there will be 7k. Multiples of 6 will be 6k. Okay, and that gives you your times tables. Yeah, 6 times 1, 6 times 2, 6 times 3, 6 times 4 gives you a 6 times table. Consecutive numbers, if you start with n, then the number after it is going to be n plus 1. The number after that will be n plus 2, and so forth. And that tells us about the consecutive numbers. Square numbers, naturally, you'll have k squared, so 1 squared, 2 squared, 3 squared, and that just means, so if you write them the first couple, 1, 4, 9, 16, 25, 36, and so forth. Rational numbers are when numbers can be written as a over b, where a and b are actual integers, and therefore we have rational numbers. Accepted facts are things like the sum of angles in a triangle add up to okay, so you don't need to go around proving that. You don't need to construct a proof if you had to use that. You can assume that's accepted. You can assume perpendicular lines have a gradient of, if I just write down, perpendicular lines have a gradient of m and 1 over m. And proven results and laws, things like index laws, the indices.
So what would be minus 1?
Yeah, so that would be, so minus 1 over m. Yeah. So the index laws, or we could have the log laws, which we haven't covered yet, which you do in C2. Or things like the discriminant equals b squared take away 4ac. You don't need to go around proving that, but that gives us the nature of the roots. Okay, theorems, okay, are things like Pythagoras, which you know, Pythagoras, the circle theorems, and also trig identities. Okay, so that's a sort of those are the sort of questions, the areas where we can assume that they're sort of given, and we don't need to go around proving Pythagoras' theorem, for example, and we can learn to express things like consecutive numbers, multiples, odd and even numbers, and so forth. Yes?
What did the second line say?
Perpendicular lines have a gradient of m and minus 1 over m. Or, said differently, have a gradient of m and minus 1 over m, i.e. if you multiply them, m1 times m2, you get minus 1, in other words. Okay, you don't need to prove that, you can assume it's given. Alright, so it's worth noting there are different types of proof. There's a direct proof, which is also known as proof by deduction. We'll be doing that in C1. Mainly it is proof by deduction, where each step follows from a previous one using accepted facts or results. There's proof by exhaustion, where you can test every possible combination. So if they say, for example, the numbers from 1 to 10 add up to this, or this happens when you multiply them by an even number, you can actually test every single case. Right? We don't do more, that's more C3. Proof by contradiction, that's a bit more complicated, where you assume the statement is not true and then prove that this assumption is false and therefore the original statement must be true. Again, that's more C3. And disprove by counterexample, where you find one case in which the statement is not true, and therefore this, you can say therefore there's evidence to suggest that this is not true. We might do a bit of disprove, but mainly the type of proofs we'll be looking at are more of the direct proofs, where show that this happens. Okay, and possibly a few examples of disproof by a counterexample. Okay, so that's essentially what we'll be doing. Right, so your first task is to take any 3 consecutive even numbers, okay, and add them together. And what I'd like you to do is tell me what you notice about their total. Off you go, I'll give you a minute. Go over a couple of examples. Right, Adi's table, what do you have? Give me an example. Tell me like an example.
4 plus 6 plus 8.
Alright, let's go over what we found. So you got 4 plus 6 plus 8 gives you
18.
18. Anybody else? Can throw
4 plus 6 plus 8.
done that one.
6 plus 8 plus 10.
6 plus 8 plus 10 gives you. Okay. What else do we have?
10 plus 4 plus 14.
Sabiha's group. And that gives you 30. Okay, what else?
10 plus
James?
I'm just do 2 plus 4 plus 6.
Okay. What's the pattern?
They're all multiples of 6.
They're all multiples of 6.
Yeah.
All multiples of 6.
That's crazy.
Yeah? How have you come up? Why wouldn't you say they can all be divided by 2 or they're all even? Why multiples of 6?
Obvious.
6 is the biggest number that they can be divided by.
Right, 6 is the biggest number, isn't it? So if you take the smallest possible even numbers, 2, 4, 6, you get 12. And yeah, they can all be divided by 2. They're all even, but 6 is the highest multiple that fits in all of them, isn't it? Now, what we want to do is be able to prove this theory using some algebra. So this is what we'll do now. Let me stick this example in. Okay, and what we want to be able to do is show that the sum of any 3 even consecutive numbers is always going to be a multiple of 6. Now we can start doing this by the first 3. Let's construct 3 numbers which are even. Okay, so if I've got some integer, n is a whole number, then we know 3 consecutive numbers, even numbers, will be 2n, 2n plus 2, 2n plus 4. Agree?
Yeah.
Right. If we were then to add them together, so let's add them, we'll get 2n plus 2n plus 2 plus 2n plus 4. This gives us 6n plus 6, where we can factorize this out. So you've got 6n plus 1, and therefore this proves that the total must always, so let's write this down, therefore the total must always be a multiple of 6. Do you see how we've constructed that? What I'd like you to do is have a go at doing something similar. So I'll leave that there so you can copy it down. Now have a go at doing this one here, where you've got the product of any three consecutive numbers, even numbers, sorry, is always a multiple of 8. Off you go. Let's resume. Okay, so the product of any three consecutive even numbers, firstly we can write the consecutive even numbers as 2n, 2n plus 2, and then 2n plus 4. If we then take the product and multiply them together, you've got 2n times our 2n plus 2, okay, times this 2n plus 4. And we can tie that up by factorising, so you've got 2n times 2n plus 1, and then times 2n plus 2. And then you've got 2 times 2 times 2, which gives us the 8n. And then you're left with an n plus 1 inside and an n plus 2 inside. And therefore, from here we know that 8 times n plus 1, n plus 2 is going to be our answer. Therefore, the product must always be a multiple of 8. So let's write down, therefore, the product is always a multiple of 8. And it goes like this. So let's take two odd numbers. It's quite interesting how you can do it this way. Two odd numbers, x and y. Then it follows that x minus 1 and y minus 1 are both even. Notice how I'm explaining it. I'm not assuming the examiner knows what I'm doing. I'm actually saying that they are even or they're odd. And what I could do is just play around with some numbers and say, well, if x minus 1 is some number, I'm going to use this 2 here deliberately, and I'll call it p. Instead of writing p, I'll write 2p deliberately, as you'll see in a minute. And y minus 1 equals 2q, okay, where p and q are just whole numbers. P and q are whole numbers, yeah, integers. Okay. And so therefore I can rearrange this and say x is 2p plus 1 and y equals 2q plus 1. And therefore the product, which was the original question, x times y, is going to be 2p plus 1 times by 2q plus 1. And if you multiply that out, we get 4pq plus 2p plus 2q plus the 1. Now do you see the point in using the algebra at this stage, where you've introduced these letters of p and q? Had we not put the 2's there, you just get p times q, but they're just integers. But when you've got the 4, because we put the 2 in front, we end up with this 4 over here. And we know that an even, so let's write this down, even times even gives us what? Even. Right. Even times odd. Even times odd, and you just try it out, so 3 times 2 will always give you an even. What about an odd times an odd? Yeah, so 3 times 3 will always give you an odd. And because we've got this even number in here, we know this must be even, that must be even, that must be even, and then therefore they all add up to give you an even number. But because we then add the 1, the final one over here, it will give us an odd number. So maybe we should write that down. That 4pq, 2p, 2q are all going to be even. Okay, and therefore the sum is going to give us an even number. And then we know an even plus 1 is always going to be odd, and therefore x times y is always odd.